So in part 10 of 11, we are going to be looking at the other main type of sequence and series. In part 9, we will look at the arithmetic sequences and series, where the arithmetic sequences are what you get if you take a pattern of number, or if you produce a pattern of numbers by adding the same number to it every time, such as 1, 2, 3, 4, 5, where you're just adding 1 each time. And then the series is when you add up all the terms in that sequence. The geometric sequences and series are similar. So with the geometric sequence, you are multiplying by the same number every time. So you could have 1, 2, 4, 8, 16, 32. Why did I write 36? I was saying 30 and got 30 on my brain. 64, and so on, where you're multiplying by 2 every time. And again, the series is the sum of these. And with an arithmetic series, and with an arithmetic sequence as well, but especially with the series, we're only really dealing with a finite series. So there's going to be some finish line we never cross. With a geometric series, if this number we multiply by every time, called the common ratio, if that has an absolute value less than 1, for example, 1/2, then we can have an infinite series that has a finite answer. For example, 1 plus 1/2 plus 1/4, 1/8, 1/16, and so on, that adds up to 2. You have to include the infinitely many terms to get there, but it has a finite sum of 2. And in fact, 1 over the sum of n minus 1, if you just keep adding up all of these, then you're going to end up with finite numbers. If you do the alternating sequences, so for example, if you did, let's say you did 1/4 plus 1/16, right? So 1 plus, and add all these up. If you're doing this, it actually truncates to a smaller sequence. You'll get a different answer if you change the signs and add and subtract them. So, they will eventually work out. But we'll be dealing with a lot of these infinite sequences and series. So just as the more concrete example, if you do 1/4 minus 1/16 plus 1/64 minus 1/256 in your calculator, compare it to the sums, you will see that every time you add another term, it gets closer and closer to a recognizable fraction. So this is actually going to eventually add up to 1/3. Whereas if you alternate, you get 1/5. Sorry. So if you have the 1/n and you keep adding those up, adding every time, then you get 1/n minus 1. But if you have your powers of 1/n and you add, subtract, add, subtract, add, subtract in what's called an alternating sequence, then you get 1/n plus 1. You can even use these infinite sequences and series to prove that 0.9 repeating is exactly equal to 1. This is one of the reasons why mathematicians don't like working with decimals. They prefer the exact values to be written as rational numbers, so as fractions. That's because the way you write a reduced fraction is unique. Now, it could be equivalent to other unreduced fractions, but once you've reduced it all the way, there is one and only one way to represent it. But with decimals, there's more than one. So these infinite sequences and series are what is going to lead us to that particular preference in dealing with exact values.